I think the Higgs boson is the biggest scientific discovery in my lifetime, and it stands with the great scientific discoveries of all time. Discoveries like the discovery of the electron, the discovery of atoms. The reason is that this is genuinely fundamental. I mean, it's been the cornerstone of much new research. The theory says, and it's been around since the 1960 seconds, by the way, this theory says that the universe is full of Higgs particles. So that means a piece of space in front of me now, and indeed inside me, and in every piece of space out to the edge of the universe is crammed full of these Higgs particles and the things that make up you and me and our bodies, and everything we can see are bumping into them. And in that process they acquire mass, which means they're solid, which ultimately means that we exist. So it's absolutely genuinely important foundation for science. It's a very beautifully simple theory. Although it sounds very odd, but I think that the act of building this thing, the Large Hadron Collider, the most complex machine ever built to go and test this theory, and then to find that it's actually true. It's actually genuinely right. I think it's quite remarkable. Right, so let's take that simple, audacious statement and unpack it carefully, because it's one of those ideas that sounds like science fiction until you see how straightforward it is when nature is allowed to speak. The claim is that empty space is not empty. It is filled everywhere and always with a field, the Higgs field, that has a non-zero value even in the quietest possible state of the universe. That quiet state is what physicists call the vacuum. If you like pictures, imagine the vacuum not as a sterile void, but as an invisible ocean with a very particular property. It is perfectly uniform. It doesn't surge or ripple on its own, but it is there, and all the elementary particles you've heard of, electrons, quarks, the W and Z bosons, move through it and crucially interact with it. That interaction is what we call mass. It is worth dwelling on that word interaction because it rescues us from a common misconception. Mass, in the modern view, is not a mysterious substance poured into particles like sand into a sack. It is a measure of how strongly a particle couples to the Higgs field. The stronger the coupling, the more the particle feels, the ever-present field, the more it resists acceleration and the heavier it is. An electron's coupling is small, a top quark's coupling is large. Photons, the particles of light, do not couple to the Higgs field at all. They glide through the vacuum ocean untouched and remain massless. Gluons, the carriers of the strong force, are also massless for similar symmetry reasons. But the W and Z bosons, which mediate the weak nuclear force, couple strongly to the Higgs field and are heavy. Without that heaviness, the weak force wouldn't be weak, it would be long-range like electromagnetism, and the universe would be profoundly different. Radioactivity would not proceed as it does, the chemistry of stars would be altered, and the chain of events that leads to a complex periodic table and ultimately to life might never ignite. Now, if space is filled with a field, where does the Higgs boson come in? Fields and particles in quantum theory are two faces of the same coin. A field is the thing that's everywhere, and its particle is the smallest ripple you can excite in that field. You can think of the Higgs boson as a tiny quantized wave, an excitation on top of the smooth background value of the Higgs field. That background value is itself an extraordinary number, about 246 giga-electron-volts, in the units particle physicists use to measure energy and mass. That is the vacuum expectation value, the level at which the field settles throughout all of space. Shake that field just right with enough concentrated energy in a particle collider, and a small transient ripple pops up. That ripple is the Higgs boson. It's unstable. It exists for a vanishingly short time and then decays into other particles. But for an instant we have made the field ring, and by studying the pattern of its ringing we learn the properties of the field itself. How do you shake a field that hard? You build the Large Hadron Collider and you engineer the most intense, highest energy proton-proton collisions humanity has ever produced. Protons are accelerated to near the speed of light in opposite directions, and then steered into head-on collisions inside massive detectors named ATLAS and CMS. Most of the time, those collisions are messy fireworks of familiar particles. Very rarely, the concentrated energy produces the precise conditions to excite the Higgs field. In practice, the principal route is a process called gluon fusion. Gluons inside the colliding protons interact via quantum loops involving heavy quarks. Most importantly, the top quark, and the end result is a Higgs boson emerging from the vacuum as if conjured. There are other routes too, vector boson fusion, where the W or Z bosons radiated by the protons interact, an associated production where a Higgs comes out alongside a W or Z or top-anti-top pair. Each pathway leaves a slightly different signature in the detectors, and the art of discovery lay in disentangling these rare patterns from a sea of lookalike events. Once created, the Higgs boson immediately falls to bits, to borrow the charming phrase. It can decay into two photons, two Z bosons, one possibly off-mass shell indicated by a star in the textbooks, two W bosons, a bottom quark and its antiquark, or a pair of tau leptons, among other things. Each decay mode is a different window on the Higgs field's couplings, how strongly it talks to the carriers of the weak force, to the fermions like quarks and leptons, and even indirectly to the photon via loops of virtual heavy particles. In 2012, when Atlas and CMS announced the discovery, the cleanest early channels were the 2-photon mode and the 4-lepton mode from Z boson. Decays rare, but exquisitely reconstructible. Over the years, the experiments have ticked off the others one by one, weaving a tapestry of evidence that the new particle behaves just as the standard model of particle physics predicted. It weighs in at about 125 giga-electron volts, roughly 130 times the proton's mass, and its spin is zero, making it a scalar particle precisely as the mechanism requires. What mechanism? This is the point where a single conceptual step takes us into deep territory. The standard model is at heart a theory with elegant symmetries. Those symmetries left intact would force particles like the W and Z bosons to be massless. But the world is not like that. The trick is spontaneous symmetry breaking. Imagine a perfectly round wine bottle standing on a table with a cork balanced upright on its top, completely symmetrical. Tip the cork the tiniest amount, and it falls into one direction, choosing a particular orientation, and the symmetry of the arrangement is hidden, not because the bottle changed, but because the ground state, the configuration, the system, settles into picked a direction. The Higgs field does something very similar. The underlying equations possess a symmetry that unifies the weak and electromagnetic forces. When the universe cooled after the Big Bang and the Higgs field settled into its non-zero vacuum value, the symmetry was hidden. The W and Z bosons acquired mass by eating the would-be massless excitations in the Higgs field, the Goldstone modes, while the photon remained massless. Out of one unified picture emerged the familiar separation between electromagnetism and the weak force with very different properties. A subtle but beautiful feature follows the strength of a particle's coupling to the Higgs field is proportional to its mass. That's why the top quark, the heaviest known elementary particle, interacts so strongly, and it's why the Higgs decays prefer heavy products when kinematics allow. It's also why neutrinos, whose masses are astonishingly tiny compared to everything else in the standard model, present a puzzle. In the simplest version of the theory, their couplings to the Higgs would have to be ludicrously small to produce such tiny masses. Many physicists suspect there is additional structure, a seesaw mechanism with heavy right-handed neutrinos, far beyond the LHC's reach, that explains neutrino masses while leaving the Higgs story intact. If so, the Higgs field is a participant in a wider neutrino sector that touches on the matter-antimatter asymmetry of the universe, and perhaps even the origin of the cosmic neutrino background, tantalizing threads not yet tied. There is another healthy corrective to a common simplification. The Higgs doesn't grant mass to everything. Most of the mass of you and me is not in the electrons, but in the protons and neutrons within our atoms, and their masses are dominated not by the tiny masses of the quarks inside them, but by the energy of the strong force that binds those quarks together. Quantum chromodynamics, the theory of the strong force, traps quarks in a buzzing confined state where the energy in the gluon fields contributes the lion's share of a nucleon's mass via E equals mc squared. So the Higgs field is essential for giving quarks and electrons their rest masses, and for differentiating the weak force from electromagnetism, but the heft of ordinary matter is remarkably mostly the energy of interaction itself. Nature is generous with ways of making mass. What does discovery deliver beyond confirmation? First, it turns a speculative idea into measured reality. We can now ask sharper questions. Does the Higgs boson couple to each fermion exactly in proportion to its mass, or are there subtle deviations? Is there only one Higgs, or are there cousins, additional scalar or pseudo-scalar particles lurking at higher energies? Do the Higgs bosons interact with themselves with the strength predicted by the standard model? That self-coupling is encoded in the shape of the Higgs potential, the energy landscape of the field, and measuring it requires observing two Higgs bosons produced in a single collision, an extraordinarily rare process. As the LHC gathers more data and upgrades its luminosity, we should begin to map that feature. It's not an academic detail, the Higgs potential touches on cosmology. The measured Higgs and top quark masses together suggest that our vacuum may be metastable, stable for inconceivably long times, longer than the age of the universe by vast factors, but not the deepest possible minimum of the potential. If that reading holds up with more precise measurements, it casts a curious light on why our universe is perched where it is on the energy landscape. It doesn't imply doom, it invites explanation. Second, the Higgs might couple, however feebly, to particles outside the standard model. This is the idea of a portal. If there are dark matter particles that interact with us only through gravity and the Higgs field, then the Higgs could occasionally decay invisibly into them, stealing energy from an event, in a way careful accountants at Atlas and CMS can detect as missing transverse energy. Alternatively, heavier Higgs-like states in extended theories, supersymmetry for instance, or composite Higgs scenarios, where the Higgs is not elementary, could reveal themselves in deviations in production and decay rates. So far, the Higgs looks comfortingly standard model-like, but every extra decimal place in the measurements is another door tested. Precision is the new frontier as much as energy ever was. Third, by testing the Higgs sector, we confront the hierarchy problem. Why is the Higgs mass so much lighter than naive quantum corrections would drive it? Quantum fluctuations tend to push scalar masses up towards the highest energy scales in the theory. In the standard model taken alone, the Higgs mass looks unnaturally fine-tuned. Delicate cancellations must occur to keep it at 125 giga-electron volts, rather than, say, up near the Planck scale, where gravity roars. Supersymmetry was long favoured as a principled solution. New particles partner each known particle and cancel the dangerous quantum contributions. Thus far, no superpartners have appeared, at least not where many expected them. Perhaps they are heavier. Perhaps the answer is different. Extra dimensions that modify the running of couplings or the Higgs as a composite of smaller constituents bound by a new force. Or perhaps nature simply accepts the fine-tuning and our task is to describe it, not to judge it. The point is that the Higgs discovery sharpened this question from philosophy to measurement. One of the quiet joys of this story is its unity with the rest of physics. The same mathematics that describes superconductors, the way electrons pair up and move frictionlessly through a metal at low temperatures, is echoed in the language of the Higgs mechanism. In a superconductor, the electromagnetic field effectively acquires a mass inside the material. Light cannot penetrate far, which is why magnetic fields are expelled. In the electroweak theory, the W and Z acquire mass in empty space because the Higgs field's vacuum value plays a role analogous to the condensate in the material. Different systems, different scales, but a shared pattern, symmetry hidden by the state the system chooses to live in. There is something deeply satisfying about that. Nature uses the same logic from the lab bench to the cosmic horizon. And then there is the sheer human achievement. The detectors that saw the Higgs are among the most sophisticated instruments ever built. Atlas and CMS are cathedral-sized, multi-layered machines with silicon trackers that can reconstruct the paths of charged particles with micron precision calorimeters that measure energies with astonishing fidelity and trigger. Systems that sift through 40 million collisions every second to select a few hundred to record. The accelerators that feed them are works of art radio frequency cavities that push protons gently turn after turn until they skim along at a hair's breadth from light speed. Cryogenic systems that keep magnets colder than deep space. Alignment systems that hold the beamlines steady to fractions of a millimeter over kilometers. All of it orchestrated by international teams that span continents and careers. When we say the Higgs discovery took 45 years, we're counting not just the physics, but the building of a global scientific culture capable of listening for a whisper in the heart of a storm. Where does it lead? It leads to the confidence to ask bolder questions. Could the Higgs field have driven an early burst of accelerated expansion, cosmic inflation, if coupled differently? Is there a link between the Higgs sector and the mystery of dark energy, the gentle pressure causing the universe to expand ever faster today? Most likely the answer to the latter is no within the standard model. The energy density associated with the Higgs vacuum is far too large if taken at face value, and yet gravity is almost insensitive to it. That mismatch is the cosmological constant problem, one of the deepest in theoretical physics. The Higgs doesn't solve it, it illuminates it. By putting precise numbers on the Higgs mass and couplings, we make the tension between quantum fields and gravity more concrete. That is progress. And there is a more immediate path, measure, measure, measure. The LHC's future runs aim to collect an order of magnitude more data, refining every Higgs coupling. There are proposals for dedicated Higgs factories, electron-positron colliders, tuned to produce Higgs bosons cleanly and copiously, allowing percent-level or better tests of the standard model's predictions. There are plans to probe the high-energy frontier even further, with hadron colliders of unprecedented scale. Each of these machines, if built, will be justified in no small part by the Higgs. We have met a new player in nature's cast, and we would like to know its lines by heart. If you love science with that combination of imagination and respect for evidence, this is why the discovery feels so beautifully fundamental. It is not only that it answers a question posed in the 1960s, it is that it shows decisively that the world really is written in the language of fields and symmetries, and that we strange apes on a small planet can read a few lines fluently enough to predict a new particle and then go and find it half a century later. The Higgs field is now part of our everyday description of reality, whether we're calculating the lifetime of a star or designing an instrument for the next collider. In that sense, it is like the electron or the atom, not a curiosity but a letter in the alphabet of the universe. And perhaps the most wonderful thing is that the story remains unfinished. The standard model with a Higgs is a spectacularly successful theory, yet it leaves dark matter unexplained, gives us no reason for the pattern of quark and lepton masses, and sits uneasily with gravity at the smallest scales. The Higgs discovery doesn't close a book. It opens several. It tells us that the path we've been walking is the right one, and invites us to continue one careful step at a time towards a wider view. In the meantime, it lends solidity to everything we are. The particles that make you and me exist as the particular tangible things they are, because the universe is full of a quiet field everywhere at once doing its work silently. That is an idea worthy of the great discoveries, and a reminder that fundamental understanding, however abstract it seems at first, is one of the reasons we have a civilization at all. Let's carry the thread a little further and make the strangeness feel natural, because that's what good physics usually does. It takes an idea that sounds exotic and lets it settle into something almost inevitable. We said that the Higgs field is everywhere quietly on, and that the Higgs boson is the brief ripple we can coax out of it with enough energy. That already tells you something profound about the way we probe nature. When we go to high energies in a collider, we're not simply smashing things to bits like clumsy giants. We're playing the universe like an instrument. Each setting of the energy, each pattern of beams and detectors is a different way of plucking a string in the quantum symphony. The note we call Higgs has a very particular pitch and a very particular harmony with the other notes. And it's by listening for that harmony, by checking how it couples to W and Z bosons, to bottom quarks and tau leptons and so on, that we've really heard the right thing. There is a beautiful economy in how those couplings are arranged. In the standard model, the strengths are not arbitrary. They are fixed by a simple rule. The heavier the particle, the stronger its coupling to the Higgs field. That's why the boson we discovered decays more readily into heavy products if kinematics allow, and why the production of the Higgs so often involves the top quark sitting quietly in the quantum loops despite the top rarely appearing explicitly in the final state. So when the experiments first observed decays into pairs of Z bosons that themselves decayed to pairs of electrons or muons and into two photons through loop effects, it wasn't because those are the most common ways the Higgs dies, because they produce clean reconstructible signatures, a quartet of charged leptons with crisp tracks, or two narrow photon showers in the calorimeters that stand proud above the messy background. Only later, with more data and improved analysis, did the collaborations tease out the more probable but trickier decays into bottom quark pairs and tau pairs, and then take on the delicate business of seeing the Higgs whisper to the muon a probable but trickier decays, a much lighter lepton. Each tick on that list is not just another trophy, it's another test of the rule mass, sets the coupling. There's subtlety in the details. Although we speak of the Higgs giving mass, it would be more accurate to say that the Higgs selects a way for the electroweak symmetry to be hidden while preserving its predictive power. The equations that unify electromagnetism and the weak interaction are symmetric and elegant when written at high energies, but the state our universe chose when it cooled, and the Higgs field settled into its non-zero value, hides that symmetry. The photon remains massless because it corresponds to a direction in the electroweak symmetry that is left unbroken, whereas the W and Z correspond to directions that are broken and they acquire mass. The three massless excitations you might expect from breaking a continuous symmetry, the Goldstone modes, are not seen as separate particles. They are eaten by the W and Z to become their longitudinal polarization states. That is the Higgs mechanism in its most succinct form. It reads like a conjuring trick when you meet it for the first time, but you can trace each step and see that nothing mysterious has been inserted by hand. It all follows from asking the symmetry to survive in the equations while allowing the world to look the way it does. If you like pictures, think of the famous Mexican hat potential. The energy of the Higgs field as a function of its value looks like a brim with a circular valley. The top of the hat, the perfectly symmetric point at the center, is unstable. the field rolls down and settles somewhere on the brim. The underlying circular symmetry remains true, but the particular resting place hides it. Fluctuations along the brim would be massless goldstones, and the fluctuation up and down the brim radially is the massive Higgs boson. That's the shape we are in a very literal sense, trying to measure with the collider, not just where the valley is, the vacuum value and how steep it is there, the Higgs mass, but whether the curvature and self-interactions of the field have the precise form predicted by the standard model. It is here that the next decade becomes particularly exciting, because to map the shape, you must watch the field interact with itself. In practice, that means producing two Higgs bosons at once. In the standard model, this is rare buried beneath more common processes, but with enough collisions and clever analysis, we can begin to see it. The rate at which Higgs pairs are produced reveals the Higgs self-coupling, and that tells us about the contour of the hat. Why should you care about the contour of a metaphorical hat? Because the shape of the Higgs potential influences the history and fate of the universe. There's a delicate interplay between the measured mass of the Higgs, the mass of the top quark, and the strength of the interactions at high energies. When you run the equations upwards, asking how the parameters evolve, as you imagine probing nature at ever higher energies, you find that for the measured values, the vacuum of our universe might be metastable, not the deepest possible valley, but a very long-lived perch. Long-lived is an understatement. The lifetime calculated from these numbers dwarfs the age of the cosmos so absurdly that there is no apocalyptic implication at all. But the near criticality is interesting. It hints that our universe sits close to a boundary in the space of theories, and close to a boundary is where phase transitions and new structures often lurk. Whether that's a coincidence or a clue is one of those questions that healthy science keeps open. Now, there is a practical frontier to all of this, and it's not only about higher energy, it's also about higher precision. The Higgs boson is predicted to be a very narrow particle. Its natural line width, its intrinsic lifetime expressed as an energy, is only a few millionths of a billion electron volts in the units particle physicists prefer. That is so narrow that the LHC cannot resolve it directly. Instead, the experiments measure the rates of different production and decay modes with increasing accuracy, and they look for consistent patterns. They also use clever avenues off-shell production of heavy boson pairs, for example, to put bounds on the total width. This is detective work. A simple way to phrase the goal is, does every measured coupling scale precisely with mass, and do the production and decay rates, when all considered together, close the books? If there is a deficit or a surplus, is it explainable by known uncertainties, or does it suggest new particles running in loops or tiny branching fractions into invisible things? This last possibility is especially tantalizing because the Higgs could be a portal to sectors of nature that are otherwise almost silent. If dark matter couples to the Higgs field, even so faintly that the only sign is that some Higgs bosons decay into invisible particles that slip through the detector, then a pattern of missing energy could betray that link. The same is true of hidden valleys, hypothetical collections of particles that interact weakly with ours. To date, the numbers are consistent with the standard model. That isn't disappointing, it's guidance. Every new decimal place pushes the design of future machines. You'll hear talk of Higgs factories, which are colliders designed to produce a very clean sample of Higgs bosons, often by colliding electrons and positrons at energies where the Higgs is produced alongside a Z boson. In such an environment, the bookkeeping becomes exquisite. You've made a Higgs, even if it decays invisibly, because you can fully reconstruct the partner Z and infer the rest from momentum conservation. The precision available there complements the brute force reach of very high energy hadron colliders that can search directly for heavy new particles. Between those two approaches, precision and reach, you cover a wide swathe of possibility space. There's also a conceptual frontier that the Higgs discovery sharpened rather than softened the question of naturalness. In quantum field theory, scalar particles like the Higgs are famously sensitive to quantum fluctuations. Virtual particles in the vacuum, those ever-present excitations allowed by quantum mechanics, tend to push the mass of a scalar up towards the highest scale in the theory. If you take the standard model as a complete description, all the way up to unimaginably high energies, you find that to keep the Higgs mass at the measured value requires precise cancellations between large quantum contributions, fine-tuning. Some physicists are content with that as a fact about our universe. Others suspect it is a hint that there's more structure. Supersymmetry was perhaps the most popular candidate for many years. It pairs every known particle with a heavier partner of different spin, and those partner contributions cancel the dangerous divergences. It's an elegant idea with other benefits, unifying forces providing dark matter candidates, but so far, the LHC has not revealed such partners in the mass ranges many expected. That doesn't kill the idea. It reshapes it, pushing parameters around and suggesting different corners to explore. Other proposals involve the Higgs being composite built of smaller constituents bound by a new force, so its mass is dynamically protected, or involve extra spatial dimensions in which the behavior of fields changes in ways that soften the problem. None of these possibilities are ruled out, none are yet required. The point is that the Higgs discovery made the question precise and empirical. We can now ask the universe to show us its cards, rather than arguing from taste. Another frontier flows from the fact that the Higgs sector can plausibly carry the kind of asymmetries and phase transitions that the early universe might have used to choose matter over antimatter. Today there is far more matter than antimatter in the observable universe. The standard model does include sources of CP violation, tiny asymmetries between matter and antimatter in certain decays, but not enough, according to most calculations, to generate the cosmic imbalance we see. If the Higgs sector were larger, if there were two Higgs doublets, for instance, or additional scalar fields, new CP violating phases could appear, and the electroweak phase transition the moment when the Higgs field switched on as the universe cooled could be strongly first-order forming bubbles and walls that favour matter over antimatter. That program goes under the banner electroweak baryogenesis. It sits at the intersection of particle physics, cosmology, and precision experiments, including searches for electric dipole moments of the electron and neutron that would betray new CP violation. Again, the LHC and its successors are relevant because they can look directly for the extra Higgs-like states these models require. It's important to keep our feet on the ground as we walk into such speculative gardens. The standard model, with its one Higgs doublet, remains an astonishingly successful description of particle interactions up to energies we have probed so far. The measurements of Higgs couplings to W and Z, to taus and bottoms, and even to muons line up beautifully with the simple mass proportional rule. There are mild tensions here and there, as you might expect when pushing experimental and theoretical tools to their limits, but nothing that compels a rewrite. That in itself is deeply informative, because it tells us that if new phenomena are present, they are either heavy or weakly coupled, or both. It suggests that the road ahead is one of patience and refinement. We are now in the regime where a percent matters. You might ask quite reasonably how this esoteric business touches the everyday. One answer is philosophical, but not trivial. The Higgs field is part of the answer to the question, why do things have the properties they do? That's not a luxury, it's the foundation of all later questions. Another answer is historical. Whenever we've learned something truly fundamental about nature, that knowledge has eventually transfigured how we live, often in ways the discoverers could not have foreseen. Maxwell's equations describing electromagnetic fields were theoretical abstractions before they became the power grid, radio, and the internet. Quantum mechanics was an odd set of rules about atoms before it became transistors and lasers. The work required to discover the Higgs already accelerated technology. High-field superconducting magnets, ultra-fast electronics, giant data pipelines and algorithms that now live in hospitals and industry. And if the past is a guide, the more we understand the Higgs sector, the more likely some currently invisible line will be drawn from basic insight to practical marvel. But let me end this turn of the story where it began, with the simplicity of the idea. The vacuum is not nothing. It is a medium with a quiet structure. Particles are not little billiard balls. They are excitations of fields and mass, the heaviness that gives things their reluctance to move, the solidity you feel when you tap the table, emerges from how those excitations talk to a field that is switched on everywhere. The discovery of the Higgs boson was not merely a confirmation of a clever mechanism. It was a demonstration that the world really is made of these abstractions, and that our mathematical stories connect to reality so closely that we can predict a new particle's existence, and properties decades in advance build an instrument the size of a city to look for it, and then see it not once, but hundreds and thousands of times with precisely the behavior expected. That is a quiet kind of wonder, not the wonder of surprise, but the wonder of coherence of a universe that agrees with itself. There is more to say. We have not talked about how the Higgs interacts with the charm quark, which is devilishly hard to see, or about the rare decay to a Z boson and a photon, or about how effective field theory lets us parameterize tiny deviations from the standard model in a systematic way and fit them across many channels at once. We have only touched on the self-coupling and on the possibility that the Higgs might, through faint whispers, touch the dark sector. Each of those threads leads naturally to the next chapter, a decade of precision, Higgs physics in which small discrepancies, if they exist, will accumulate into a pattern. And patterns are how new physics introduces itself, softly at first, then unmistakably. Alright, let's press further into the Higgs story and make it feel not just true but inevitable, as if the universe could hardly have arranged itself any other way. We've said that the Higgs field is switched on everywhere. That mass is the measure of how strongly a particle couples to this field, and that the Higgs boson is the ephemeral ripple we can coax from that field when we concentrate enough energy into a tiny region of space. That is the broad picture. Now let's step closer, because the fine print is where physics becomes a craft. It's in the precise patterns, the branching fractions, the production modes, the angular correlations of decay products that nature either nods and says, yes, that's the standard model, or tilts its head and whispers, look again. Start with production, because the way we make Higgs bosons colors everything we can learn. In proton-proton collisions, the dominant path is gluon-gluon fusion. Two gluons inside the protons fluctuate into a loop of heavy quarks, most powerfully the top quark, the heaviest of all known elementary particles, and out of that loop the Higgs emerges. It's a marvelous example of the quantum world doing something classically impossible, massless gluons, assembling a massive scalar via a virtual tour through heavy matter. A second important path is vector boson fusion, where each proton radiates a W or Z boson, and those fuse to produce a Higgs. The telltale sign of that is two energetic jets flying forward in opposite ends of the detector, like sentinels with a quiet central region where the Higgs decays. Then there's associated production, where the Higgs comes out alongside a W or a Z, or with a top-antitop pair. Each of these modes is a different question posed to the Higgs sector. Gluon fusion probes the Higgs coupling to the top quark indirectly through loops. Vector boson fusion and Higgs W divided by Z production interrogate the Higgs interactions with the carriers of the weak force. Production with top quarks, though rarer, catches the top Higgs coupling directly in the act. That top Higgs interaction is fascinating in its own right. In the standard model, the coupling is essentially maximal. The top's mass is so large because it talks very strongly to the Higgs field. By studying events where a Higgs appears with a top-antitop pair, and by looking closely at the kinematics and spin correlations in those events, experiments can test not just the strength but the character of the interaction, whether it is purely scalar, as predicted, or whether a small pseudo-scalar admixture creeps in. These are subtle words. For a simple idea, does the Higgs treat left and right the same way, or does it have a tiny-handedness that would betray new physics? So far, measurements line up beautifully with the scalar expectation. But the very act of getting there, of reconstructing these busy jet-filled events and finding the gentle Higgs signal among them, is a triumph of experimental technique. Now consider decays. The Higgs is like a short-lived banker. Settling accounts, it decays along paths weighted by the square of the couplings. It prefers heavy children when allowed. That's why for a Higgs mass, around 125 times, the protons that decays into W and Z boson pairs, bottom quark pairs and tau lepton pairs dominate the conversation. The two-photon decay, though rarer, is a gem because photons are clean and the resonance appears as a sharp bump in a smooth spectrum. But that two-photon mode is also conceptually rich. It doesn't happen at tree level in the standard model. It proceeds through quantum loops of charged particles, again with the top quark and the W boson taking starring roles. Measure it precisely, and you are sensitive to any unknown heavy charged particles that might contribute to that loop and subtly alter the rate. The same is true of the rare decay to a Z boson and a photon. The numbers here are small, and the backgrounds are larger. But the payoff is real. Any consistent deviation across loop-sensitive channels would be a siren for new states. One of the most delicate triumphs in recent years has been to watch the Higgs couple to the second family of fermions, not just the heavy third family. The decay to muon-antimuon pairs is vanishingly rare, but muons are beautifully measured, and the observation of that decay is both a technical feat and a deep conceptual milestone. It confirms that the rule mass sets the coupling continues down the family tree. The charm quark is more elusive. A Higgs decaying to charm, anti-charm, looks suspiciously like one decaying to bottom, anti-bottom. Once the jets are fragmented and spread, and distinguishing them requires exquisite flavor tagging. There are clever complementary strategies as well, looking for a Higgs decaying into a specific bound state like a J divided by psi, plus a photon which would shine a different kind of light on the charm-Yukawa coupling. Piece by piece, the experiments are tightening the net. Each new constraint isn't just a number, It's a test that the Higgs really is the universal bookkeeper of fermion masses. Then there is the question of identity. When the particle was discovered, it was not enough to say there's a new resonance at 125. We had to show that its quantum numbers, the traits by which particles are categorized, matched those predicted. The spin had to be zero because the Higgs mechanism requires a scalar field. The way the decay products fly apart in space encodes that information. In decays to 4 leptons, via Z bosons for instance, the distribution of angles between the leptons is a fingerprint. By comparing data to templates, one can rule out spin-2 imposters and mixed parity scenarios. The conclusion that the boson is a CP-even scalar matching the standard model Higgs is now very strong. But very strong does not mean the end. The possibility of a tiny CP-odd admixture remains a target, and that pursuit isn't semantic. New CP-violating phases are precisely the sort of ingredient cosmology might have needed to tilt the early universe towards matter over antimatter. While we're talking identity, a quiet but powerful measurement sits in the background, the total width of the Higgs. In colloquial terms, how quickly does the particle decay summed over all possible channels? The standard model prediction is only a few millionths of a billion electron volts, so narrow that even the LHC's superb detectors can't resolve it directly. But the width matters because any unseen decay path, perhaps into invisible particles, would broaden it. The trick is to build indirect constraints by combining on-shell and off-shell production measurements. When the Higgs is produced off its mass peak, for instance, in high-mass pairs of Z bosons, the rate depends differently on the couplings and the width than it does on the peak. By fitting both realms together, you can trap the width between upper and lower bounds. The current picture is that the width is compatible with the standard model expectation, leaving little room for large invisible branches, but not yet excluding delicate portals to a dark sector. It's a game of decimals, and decimals are exactly where surprises like to hide. Precision drives us naturally to a language that theorists have honed for just this situation: effective field theory. The idea is to write the most general set of small deformations to the standard model, allowed by its symmetries, and then to fit those deformations encoded in Wilson coefficients to data. It's a disciplined way to ask whether the Higgs couplings are tilted by a percent here or there, whether the tensor structure of an interaction contains a tiny extra term, whether momentum-dependent corrections appear at high transverse. Momenta. Crucially, this approach lets you combine information consistently across many processes: gluon fusion rates and shapes, vector boson fusion distributions, associated production spectra, and all the various decay channels. You are no longer looking for a single smoking gun. You are asking whether a coherent pattern emerges. If it does, you can translate that pattern back into statements about possible heavy new particles or forces that would generate it when integrated out. If it doesn't, you tighten the cage around the standard model. Another thread that binds particle physics to cosmology is the shape of the Higgs potential, the metaphorical Mexican hat. We already measure the curvature at the minimum through the Higgs mass. The next step is to measure how the field talks to itself, the trilinear self-coupling. In the standard model, this is a fixed number once the mass and vacuum value are known. Experimentally, the route to this coupling is through Higgs pair production. Two mechanisms compete: a box diagram where gluons interact through a heavy quark loop to spit out a pair of Higgses without any self-coupling involved, and a triangle diagram where an off-shell Higgs is produced and then splits into two via the self-coupling. The two interfere, sometimes constructively, sometimes destructively, so the total rate and the kinematic shapes sensitively encode the self-interaction. It is a cruelly rare process, but the high luminosity era of the collider and perhaps future machines will squeeze it hard enough to yield a first precise determination. That number touches on questions as grand as whether the electroweak phase transition in the early universe was smooth or violently first order. If it were, the latter bubbles of the new phase would have formed and expanded, potentially generating a background of gravitational waves that future observatories could hear. It's a lovely example of how a decimal point measurement in Geneva can echo in a conversation about signals in space-time itself. All of this begs the practical question: what machines do we need? The present collider will continue to collect extraordinary data sets, pushing uncertainties down and opening channels that were once out of reach. But you'll hear lively discussion about dedicated Higgs factories, electron-positron colliders, tuned around the energy where Higgs Z production is maximal. In that clean environment, you can catch the Z boson unambiguously and infer the Higgs's presence, even if it slips invisibly away, allowing absolute coupling measurements with percent-level precision. You'll also hear about circular colliders that would later be upgraded to very high-energy proton machines, combining precision with discovery reach. Muon colliders are an exciting, more futuristic idea because muons are point-like and heavy. One could, in principle, scan directly over the Higgs resonance in the S-channel with exquisite energy resolution, turning the machine into a spectrometer of the Higgs line shape itself. Each proposal reflects a philosophy of how to learn. Either you count and measure very cleanly, or you push to energies where new heavy states might sit. In practice, the field will likely do both, as it has always tried to. There is also a connection to flavor the pattern of masses and mixings among quarks and leptons that the Higgs brings into sharp relief. In the standard model, the Yukawa couplings are just numbers we fit. The electron gets this one, the muon that one, the top quark a very large one. The pattern is strikingly hierarchical, spanning many orders of magnitude, and no one knows why. There are ideas. Perhaps new symmetries are at work, broken in careful ways. Perhaps the geometry of extra dimensions or dynamics of new strong sectors distribute the couplings unevenly. However, it plays out. Measuring the Higgs interactions to as many fermions as possible across families is our experimental handhold on the problem. The discovery of the muon decay is one rung on that ladder. Charm will be another. If we could ever see an electron-Higgs interaction directly, fantastically difficult at present, it would be a kind of punctuation mark. A muon collider again is attractive precisely because it upgrades a second-generation lepton from spectator to protagonist. The Higgs would be produced directly through the muon Yukawa. Sometimes the route to understanding is to choose a machine that makes a particular coupling impossible to ignore. Before we drift too far into the horizon, it's worth returning to the standard model's astonishing resilience. Every careful test of Higgs couplings to W and Z bosons supports a principle called custodial symmetry, which, loosely speaking, keeps the W and Z masses in the ratio they ought to be. Deviations there would shout new physics from the rooftops. Instead, we get a measured murmur of agreement. Differential distributions, the way Higgs events populate, high transverse momentum tails, are increasingly well described by precise calculations, including higher-order quantum corrections that would once have been state-of-the-art, all by themselves. Even the inclusive rate for producing a Higgs through gluon fusion, long a stern test of our ability to compute with quarks in loops, is now mapped with impressive accuracy. The point is not to say nothing to see here. It is to recognize that the more solid this edifice becomes, the more any hairline crack will matter. A 1% deviation, if robust, will be a headline. And then there is the human note, because physics is a human activity, and its achievements reflect not just ideas, but communities that learn to build, to calibrate, to criticize kindly, and to persevere. The instrumentation developed to weigh and watch the Higgs fast-timing silicon sensors, high-field superconducting magnets, novel pattern recognition algorithms, has a life outside the laboratory. Medical imaging, radiation therapy, materials science, and data-intensive industries adopt and adapt techniques born from the desire to see a short-lived scalar in a storm of debris. That is not a justification for fundamental science. It is simply a fact about how knowledge propagates. We push the boundaries of understanding because it is what a curious species does. The dividends arrive unannounced. If I had to compress this chapter into a single thought, it would be this. The Higgs sector is no longer a rumor. It is a measured landscape. We have the coordinates, the mass, the dominant couplings, the spin and parity written down with increasing precision. We have a map of the paths to explore next self-interactions, second generation, Yukawas, rare, loop-sensitive decays, and the worldwide program of precision fits that can reveal a pattern long before a single glaring anomaly appears. The excitement now is not in the shock of discovery, but in the possibility that by listening carefully to the harmonies, we might hear a new instrument enter the orchestra from the wings. Perhaps it will be a faint extra scalar, a whisper of CP violation, or a consistent tilt across high momentum tails that points to heavy states beyond our direct reach. Or perhaps the score we have is complete at these energies, and we will need to turn the page to a higher scale to find the next theme. Either way, the Higgs has taken what used to be a gap in our understanding, the origin of mass for the W and Z bosons, and for the fundamental fermions, and turned it into a working piece of machinery. It does not just explain, it predicts, and we can test those predictions. That is what it means for an idea to pass from audacity into physics. Let's keep walking, because the Higgs story opens like a landscape at dawn. The longer you look, the more detail emerges, and the more that detail makes the whole feel inevitable. We've talked about the headline, the field switched on everywhere, the scalar ripple we call the Higgs boson, the way mass is really a measure of coupling rather than a dollop of stuff. And we've dipped into the experimental craft that allowed us to hear that ripple in the roar of proton collisions. Now I want to widen the frame and then narrow it again, because the Higgs sits at a crossroads. It touches deep theoretical questions about symmetry and naturalness. It connects to cosmology through phase transitions and the possibility of hidden sectors. And perhaps most tantalizingly, it gives us a dial-self interaction that we've only just begun to turn. Begin with a common confusion that's worth untangling carefully. Does the Higgs give mass to everything? The honest answer is no and yes. No, in the sense that most of the mass of ordinary matter, protons and neutrons, is not the sum of the tiny masses of the up and down quarks inside them, but rather the energy of the strong force field confining those quarks. Quantum chromodynamics binds quarks so fiercely that the gluon fields themselves carry energy, and by Einstein's equation, energy contributes to inertia. So when you hold your hand up, most of what you feel resisting, gravity is the energy of interaction, not the Higgs directly. And yet the yes is equally important. The Higgs gives the quarks and leptons their rest masses and makes the W and Z bosons heavy. Without that, atoms would not be atoms as we know them. Chemistry would be unrecognizable. Stars would live different lives, and the universe would not have the same catalogue of possibilities. The Higgs doesn't shoulder the whole weight of the world, but it shapes the scaffold on which the world is built. Now, the machinery that gives the W and Z their mass has a lovely analogue in condensed matter physics, and it can help your intuition. In a superconductor, electrons pair up and move coherently through a lattice. The electromagnetic field, which ordinarily penetrates materials, acquires an effective mass inside a superconductor. Magnetic fields are expelled, the Meissner effect, and light cannot travel far. That mass for the photon in a medium arises because a background condensate breaks a gauge symmetry in a way that hides it rather than destroys it. The electroweak theory's Higgs mechanism is the high-energy cousin of this logic. The background value of the Higgs field plays the role of the condensate in empty space. The underlying symmetry survives in the equations, but the state the universe lives in hides it. The W and Z eat the massless would-be excitations and gain a longitudinal polarization, gaining heft in the process, while the photon corresponding to a preserved direction in the symmetry remains massless. Different domains of physics, the same pattern of thought. Nature is frugal with its ideas. Having confirmed the existence of the Higgs boson at about 125 giga-electron volts, we moved immediately into a new phase, turned the particle into a measuring device. That's not poetry, it's strategy. Each coupling of the Higgs boson to W and Z to bottom quarks and tau leptons to top quarks through loops to muons and eventually to charm reads off an entry in the universe's ledger, and the question is whether the entries line up with the standard model's rule, coupling proportional to mass. The results so far are a kind of symphony of agreement. The rates of production across the major modes, gluon fusion, vector boson fusion, associated production with W divided by Z, and top fit the expectations. The decays to heavy pairs are there at the predicted strengths. The 2-photon and Z-photon modes, which are loop sensitive and thus exquisitely vulnerable to contributions from unknown heavy charged particles, sit where they should within today's uncertainties. Even the whisper, quiet muon mode has been heard. That's not dull, it's profound. It says the simplest version of the mechanism is the one nature chose, at least to the level of precision we can currently muster. But precision is now the story. Consider the total width of the Higgs, which is a way of asking how quickly the particle decays, summed over every channel. The standard model predicts a width so tiny that with the energy resolution of a hadron collider, the resonance looks infinitely sharp. You can't see the width directly, so the experiments build traps out of logic. They measure the on-shell production and decay rates on the peak of the resonance, and they measure processes like high-mass Z-boson pairs, where the Higgs appears off-shell, far from its nominal mass. The off-shell rate depends on couplings in a different way, and by tying the two regimes together, you can bound the width. The picture emerging is consistent with the standard model. That's not only a tick mark, it's a squeeze on many exotic possibilities. If, for example, the Higgs were decaying invisibly a large fraction of the time into dark matter, the width would be broader and the balance of visible rates would shift. Present data say not too much invisibility, if any, but not too much is not none, and the search continues with keener eyes. This idea that the Higgs could be a portal is one of the most compelling avenues for surprise. Dark matter, if it's a particle, and that's still an if, albeit a leading one may couple to the Higgs because the Higgs couples to mass. That would allow Higgs bosons to decay into pairs of dark particles that ghost through the detector. More subtly, the Higgs could mix with scalars from a hidden sector producing cousins that decay in unusual ways, perhaps long-lived, travelling a measurable distance before decaying and leaving displaced vertices in the detector. Those would be spectacular signatures, particles popping into existence centimetres away from the collision point, like fireworks with delayed fuses. Atlas and CMS have remarkable sensitivity to such events, precisely because they've learned to spot the orderly amid the chaos. No such fireworks have been confirmed yet, but the parameter space is big and patience is part of the craft. Then there's the self-interaction, the piece of the puzzle that tells us how the Higgs field talks to itself. In the metaphor of the Mexican hat, it's the curvature of the brim in the radial direction. In the standard model, once you know the vacuum expectation value and the Higgs mass, the strength of the trilinear self-coupling is fixed. Experimentally, you access it through events where two Higgs bosons are produced at once. Two quantum pathways contribute a box diagram where gluons through a loop of heavy quarks produce the pair directly, and a triangle diagram where an off-shell Higgs is made and then splits into two via the self-coupling. The two pathways interfere. The total rate is small, and the final states you can hope to reconstruct cleanly are rare combinations like two bottom jets plus two photons, or two bottoms plus two tau leptons, or four bottoms with heroic flavor tagging. It's one of the most challenging measurements on the agenda, but it's also one of the most revealing. Get that coupling right, and you've written another line in the universe's operating manual. Find it tilted, and you've got immediate guidance toward extensions of the Higgs sector, extra doublets, singlets, or composites that reshape the potential. Speaking of extensions, there's a family of ideas, supersymmetry, composite Higgs, twin Higgs, neutral naturalness, that address one of the oldest irritations in the theory naturalness. Scalar masses like the Higgs mass are sensitive to quantum corrections from virtual particles. Left unchecked, those corrections would drag the Higgs mass up to whichever high scale lurks above the standard model, perhaps the Planck scale, where gravity can no longer be ignored. To keep the Higgs at 125 giga electron volts seems to require exquisite cancellations, fine-tuning, unless there's new structure. Supersymmetry introduces partner particles whose contributions cancel the dangerous terms. Composite Higgs models imagine the Higgs as a bound state of new constituents with symmetries that protect its mass. Twin Higgs and related ideas propose mirror sectors that restore a form of symmetry without introducing particles charged under the standard model, hiding the new physics from many searches. Each of these frameworks leaves footprints. In Higgs physics, modified couplings, new light scalars, altered high momentum tails, or rare decays. So far, the footprints we see are standard model shaped. That could mean the new structure lives at higher energies. It could mean nature tolerates fine-tuning in a way our aesthetic sensibilities do not. Or it could mean that we've not yet looked in precisely the right way. The next decade of precision is precisely an attempt to look in the right way. The Higgs also threads into the early universe, in a more direct fashion, through the electro-weak phase transition. As the universe cooled from its hot, youthful state, the Higgs field switched on, rolling from the top of the hat to the brim, and in that moment the W and Z acquired mass, and the weak and electromagnetic forces differentiated. If that transition were a gentle crossover as the standard model with one Higgs doublet predicts for the measured Higgs mass, then it likely didn't provide the violent, out-of-equilibrium conditions needed to create the matter-antimatter asymmetry in the observable universe. But if the Higgs sector is larger, if there are extra scalars, then the transition could be first-order bubble nucleation wars, sweeping through space conditions ripe for generating a bias towards matter, provided new CP-violating phases are present. That scenario, electro-weak baryogenesis, is a beautiful example of how particle physics, cosmology, and even gravitational wave astronomy can meet. Strong first-order transitions can leave a stochastic gravitational wave background that future detectors might hear. In that sense, a tiny deviation in a Higgs coupling at a collider could be a hint that somewhere very faintly the universe is still humming with the memory of its own transformation. All of this physics demands instruments matched to the questions. The current Hadron Collider will deliver an enormous harvest of data in its high luminosity era, sharpening every coupling and opening increasingly rare channels. But there's a reason you'll hear physicists speak with delight about Higgs factories. An electron-positron collider tuned to energies where Higgs Z production is maximal gives you a uniquely clean environment. You tag the Z boson with exquisite precision, and infer the Higgs even if it decays invisibly, allowing absolute coupling measurements and model-independent determinations of the total width. A circular machine could later be upgraded to handle protons at energies far beyond what we have today, marrying precision to discovery reach. A linear machine could push to higher energies for direct top Higgs studies. And then there's the audacious idea of a muon collider. Because muons are point-like and heavy, you could in principle scan directly across the Higgs resonance in the S channel and measure its line shape and couplings with unrivaled precision, turning the machine into a kind of spectrometer for the Higgs itself. Each proposal reflects a way of thinking about knowledge count cleanly or climb high. If history is a guide, we'll need both. Let me linger for a moment on a quieter frontier flavor. The pattern of fermion masses and mixings, the fact that the electron is light, the muon heavier, the tau heavier still, that quarks come in three families with a Baroque mixing matrix, that neutrino masses are tiny but not zero, is written into the Higgs sector through the Yukawa couplings. In the standard model, those couplings are simply numbers we measure and type into the equation. They work, but they don't explain themselves. Why such a hierarchy? Why the mixings we see? Many speculative ideas, horizontal symmetries, textures, Froggatt-Nielsen mechanisms, extra dimensions with wave functions sequestered in different places try to account for the pattern. Our experimental handle on the problem is to measure as many of the couplings directly as we can. We've seen bottoms and taus, we've glimpsed muons, we're circling charm. Every step pins the pattern more tightly and limits the room for new dynamics. If ever we could reach the electron directly, fantastically hard in current setups, we would add a punctuation mark to the sentence. Short of that, a muon collider offers a way to take a second-generation lepton from the chorus to the solo line. You produce the Higgs directly through its coupling to the muon, and the coupling becomes impossible to ignore. It's easy in the face of so much subtlety to imagine the field as a web of complications, but the guiding thread is still simplicity. The standard model with one Higgs doublet is not a gratuitously Baroque story. It is the minimal way to reconcile the symmetry we love in the equations with the world we observe. The long arc from the 1960s to discovery and on into the present is a testament to a method propose an elegant mechanism, work out its fingerprints in painful detail, build machines capable of discerning those fingerprints in violent experiments, and then keep measuring until the decimals either affirm the mechanism's simplicity or reveal the seams where it starts to fray. If you're fond of stories with clean endings, physics will frustrate you. The joy is in the continuation, the way each answered question refines the next one into something askable. So where are we, honestly? We have a particle, a scalar with spin 0 and even CP that weighs 125 giga electron volts. It couples to the carriers of the weak force and to fermions in proportion to their mass, to within the percent level precision we currently command. It decays with a total width too narrow to resolve directly, but compatible with the standard model when trapped indirectly. It's produced in the ways expected with differential distributions increasingly well mapped. We have first glimpses of its interaction with the second generation and first constraints on its self-interaction. We have no confirmed anomalies that force us to rewrite the textbook. And yet the textbook is not the universe. The universe is more than the standard model. It contains dark matter. It expands ever faster for reasons we label dark energy without understanding. It began in a state whose asymmetry between matter and antimatter we cannot yet explain within known sources of CP violation. The Higgs may not solve those mysteries on its own, but it is a bridge to them, a place where new threads could attach. The beauty of the present moment is that you can love the Higgs for two different reasons at once. You can love it for its calm coherence, for the way it completes the electroweak theory and puts mass on a firm predictive footing. And you can love it for the doors it leaves ajar, for the way a slight deviation in a coupling or a faint hint of an exotic decay could redraw our map of what lies beyond. That to me is exactly what fundamental science should feel, like we are not lost. We have a compass, and the horizon is still inviting. Let's keep going, because the closer you stand to the Higgs, the more the ordinary world starts to look like a carefully tuned instrument. You can feel the logic of it, the way a simple symmetry quietly hidden becomes the reason water is liquid at room temperature, the reason stars burn the way they do, the reason electrons sit still enough around atoms to make chemistry possible. The Higgs sector is not a glamorous sideshow attached to the standard model. It's the hinge that lets the doors open. We've said that mass is a coupling to a field that is always on, that the Higgs boson is the ripple we can excite with enough energy. and that the simplest version of this idea is what nature appears to use. But simplicity doesn't mean shallowness. The Standard Model's Higgs sector is like a haiku, few words, vast space. Let's walk into that space a little further first on the theoretical side, where we ask, how do we even phrase the next questions? And then on the experimental side, where we ask, how do we hear a whisper in a hurricane? On the theory front, there's a language we lean on now called effective field theory. The name sounds forbidding. The idea is disarmingly practical. You write down the Standard Model, which has passed every test we've thrown at it, and then you allow the tiniest, most general deformations, consistent with its symmetries, little dials that could tilt a coupling by 1%, or introduce an extra momentum dependence, or mix a scalar with a pseudoscalar by a hair's breadth. Each dial corresponds to a Wilson coefficient, a number that you can, in principle, measure. This approach gives you a disciplined way to ask, are we off by 1%, 2% without committing to any particular new theory? It also lets you combine diverse information correctly, the rate and shape of Higgs production through gluon fusion, the angular distributions in Higgs decays to 4 leptons, the forward jets that tag vector boson fusion, the transverse momentum tails in associated production with a W or Z, and even precision electroweak observables that don't contain a Higgs at all but feel its presence through loops. When you fit all of that together, you're not just hunting for a bump, you're asking whether a consistent tilt shows up across the orchestra. This is where the hierarchy of questions becomes important. There are the headline couplings, the Higgs to W and Z, to top indirectly and directly in association to bottom, to tau, to muon, that we measure as absolute strengths with ever-shrinking uncertainties. Then there are structure questions. Is the coupling purely scalar as predicted, or does a trace of CP odd behavior creep in? That shows up in how decay planes open and how final particles are correlated in angle and momentum. Then there are rare channels probing loops, Higgs to 2 photons, Higgs to Z and a photon. Those are exquisitely sensitive to unknown heavy charged particles that could run in the loop and tweak the rate by a few percent. And finally, there is the grand prize of subtlety, the Higgs self-coupling, which tells us about the curvature of the potential, the thickness of the brim on the famous Mexican hat. That requires Higgs pairs. They are rare, but they are the Rosetta Stone for how the field talks to itself. Now, if all of that sounds precise to the point of obsession, that's because precision is where new physics often hides once the obvious surprises are gone. The measurements you need are not single numbers, but constellations of distributions. For example, the way gluon fusion events populate the high transverse momentum region, where a recoiling jet kicks the Higgs hard, can reveal whether the top quark loop is exactly the one in the textbook, or whether additional heavy states, perhaps beyond direct reach, are silently lending a hand. The same goes for vector boson fusion. The rapidity gap between the forward tagging jets, the amount of extra radiation in the central region, the correlation between jet directions each is a lever arm on tiny departures from the Reba. Standard Model's tensor structure. This is the physics equivalent of listening for overtones on a violin string to infer the tension, the humidity, even the age of the wood. You don't just hear the note, you hear the instrument. That brings us to the experimental craft, which is both heroic and quietly meticulous. A modern hadron collider is a controlled storm. Protons meet protons at energies so high that the language of quarks and gluons is the only sensible way to speak, and in each crossing there may be dozens of simultaneous pile-up interactions layered on top of the one you care about. Yet within that chaos, a Higgs decaying to 2 photons makes 2 narrow showers in an electromagnetic calorimeter, with a resolution good enough to draw a resonance as a crisp little hill on a smooth landscape. A Higgs decaying to 4 charged leptons leaves tracks that can be fitted back to a common point to within tens of microns, and their momenta can be measured to a part in 1,000 with silicon and magnetic fields. A Higgs to bottom, anti-bottom hides in an ocean of ordinary QCD jets. Pulling it out is an art of flavor tagging where subtle differences in how a jet fragments secondary vertices from B-hadron decays. Soft leptons, embedded in the jet track impact parameters, are combined by sophisticated algorithms into a single discriminant. Machine learning techniques born in this arena now find displaced vertices, distinguish tau decays, and even reconstruct the decay of highly boosted Higgs bosons into bottom pairs, where the 2 jets merge into one broad fat jet with substructure that can be teased apart. It's detective work with 1 trillion suspects. There is a constant conversation between theory and experiment here, and the quality of that conversation matters. When the experiments measure a rate, the theorist must provide a prediction with uncertainties. You can trust higher order QCD corrections that tame the strong force's exuberance, electroweak corrections that matter at the percent level, Parton distribution functions describing how a proton's momentum is shared among its quarks and gluons, and careful estimates of non-perturbative effects. The uncertainties are not decorations, they are the measure of how much you should believe a deviation if you see one. In recent years, predictions for Higgs production have climbed to next to leading order in QCD for the most important channels, an achievement that would have sounded fanciful a decade ago. Lattice calculations inform hadronic inputs, global PDF fits incorporate new data, and the line between what is theory and what is extracted from data is carefully maintained to avoid circular reasoning. Precision is not a slogan, it's a discipline. Let's pivot to a question that often lurks just behind the polite surface naturalness. Scalar masses like that of the Higgs are sensitive to quantum fluctuations from every particle that talks to them. In a naive calculation, those fluctuations would push the Higgs mass up towards the highest scale in the theory. If that scale is the Planck scale where quantum gravity takes over, you are left with a puzzle. Why does the Higgs sit down at 125 giga-electron volts instead of climbing the staircase to a vastly higher mass? One answer is because the bare parameters conspire. Deal with it. Another answer is because there is new structure that protects it. Supersymmetry provides partners that cancel dangerous contributions. Composite Higgs ideas make the Higgs a bound state whose mass is protected by symmetries. Twin Higgs and neutral naturalness models hide the partners in a mirror sector uncharged under our forces. Extra-dimensional models distribute the fields in a geometry that softens the sensitivity. These pictures are not bedtime stories. They are calculable frameworks with consequences. If supersymmetry solves the problem, then at some energy you should find superpartners, or if they are heavy precision, Higgs couplings should carry telltale percent level shifts. If the Higgs is composite, you expect resonances at a few tera-electron volts and specific deviations in high momentum distributions. If there is a mirror sector, the Higgs might mix with a singlet, altering its branching ratios or producing long-lived states. The lack of dramatic discoveries so far has pushed these ideas into subtler corners, but it has not erased them. Naturalness has become an empirical question. The more precisely we measure, the more corners we light up. Now to cosmology, where the Higgs casts a longer, stranger shadow. The electroweak phase transitioned the moment when the Higgs field rolled off the top and settled into its valley, likely preceded as a smooth crossover in the minimal theory for the measured Higgs mass. Smooth is lovely for calculability. It's poor for making more matter than antimatter. But enlarge the Higgs sector, and you can make the transition strongly. First order bubbles, nucleating walls, sweeping through out of equilibrium conditions ripe for creating the cosmic asymmetry if new CP violating phases are present. That picture sits at the nexus of collider physics, electric dipole moment experiments, and future gravitational wave observatories, which could in principle hear the hiss of that ancient boiling if the parameters are just so. The Higgs also touches the question of vacuum stability. With the measured top quark mass and Higgs mass, a calculation suggests that our vacuum may be metastable, comfortable for unimaginably long times, but not the deepest minimum. That's not an emergency. It's a curiosity that begs for an explanation, and it makes precision on the top mass and the Higgs self-coupling more than parochial details. They decide where we sit on the map. While we're thinking big, there's the elephant in the room that the Higgs illuminates, but doesn't tame the cosmological constant problem. If you sum up the energy of quantum fields, including the Higgs naively, you get an absurdly large vacuum energy. Gravity should feel that and either blow the universe apart or snap it shut. It doesn't. The observed dark energy is tiny by comparison. Somewhere in that mismatch lies a profound truth about how quantum fields talk to gravity. The Higgs doesn't solve it, but by turning the Higgs sector from a hypothesis into a measured entity, we've made the tension more precise. Sometimes making a paradox sharper is progress. Let's turn back to the business of what to build next, because the desire to answer these questions isn't abstract. It's architectural. The present collider will enter its high luminosity era, delivering an order of magnitude more data and pushing uncertainties on many Higgs couplings towards the percent level or better. That alone is a transformation. Percent level precision turns hand-waving into surgery. But the community is also sketching machines whose very purpose is to weigh and watch the Higgs with incomparable clarity. Electron-positron Higgs factories operating where Higgs Z production is maximal offer model-independent coupling extraction and sensitivity to invisible decays, because you can reconstruct the Z cleanly and infer the Higgs as recoil. Circular designs promise enormous yields. Linear designs promise higher energies for top Higgs studies and beyond. Proton colliders at higher energies extend discovery reach into the tens of tera electron volts where heavy partners may live. And the most audacious idea, because it dances on the edge of what we can engineer, is a muon collider. Muons are point-like and heavy. Collide them with precisely tuned energy, and you can produce the Higgs directly in the S-channel, scanning across its resonance and measuring its line, shape and couplings as though the Higgs were an atomic transition. The backgrounds are different, the challenge is formidable, but the prize is a microscope aimed at the scalar itself. Each machine encodes a philosophy count with exquisite cleanliness, reach for new mass scales, or place the Higgs under a spectroscopic lens. If history is a guide, we'll aim to do all three in sequence. There's a quieter, more personal thread I want to pull. It's the flavor story, the pattern of Fermion masses and mixings written in the Higgs couplings. In our equations, the Yukawa couplings are just numbers we fit. They span many orders of magnitude for reasons we do not understand. The top quark's coupling is almost 1. The electrons is tiny. The muon sits in between. The neutrinos in the simplest version of the theory would have absurdly small couplings if they got their mass from the Higgs alone, which is part of why many of us suspect a seesaw mechanism with heavy right-handed neutrinos lurking somewhere far above our reach. Every direct measurement of a Yukawa coupling bottom and tau long-established muon now glimpsed charm in our sights turns that list of numbers from an input table into a set of observables. When you see a plot of coupling versus mass, and the points march along a straight line through many orders of magnitude, it's strangely moving. The universe, it seems, keeps its accounts with a simple rule. We have no idea why the numbers are what they are, but we can at least confirm that the same accountant wrote them all. Before we close this turn, I want to leave you with a sense of texture. The Higgs is not an isolated marvel, but a node in a network. Its discovery required superconducting magnets colder than outer space and alignment systems that keep beams on course to fractions of a millimeter over kilometers. Its analysis required calorimeters that can tell one kind of shower from another, and trackers that can see a particle's birth point displaced by a few millimeters because it came from the decay of a long-lived parent. Its interpretation required theorists to compute loop diagrams with 3 loops and resum logarithms that otherwise spoil perturbation theory in certain kinematic corners. Its future will require engineers to build cavities that accelerate muons before they decay, or to design detectors that timestamp each particle to within a few tens of picoseconds, so that you can separate genuine Higgs decays from pile-up in an environment busier than a city at rush hour. None of that is incidental. Fundamental questions call forth new tools, and those tools tend to wander into the wider world. Medical imaging borrows reconstruction techniques, radiation therapy borrows dosimetry and beam control, data science everywhere borrows pattern recognition algorithms polished inside Atlas and CMS. It's not that we do particle physics to get better scanners, it's that when you push hard on nature to answer a deep question, you often learn how to see, and seeing is useful in more places than one. So where do we stand? We have weighed the Higgs, watched it coupled to the heavy family, heard it whisper to the muon and glimpsed the edges of its self-regard in early studies of pair production. We have not yet seen it open a door to the dark sector, but we've placed our fingers on the handle. We have mapped its identity spin 0CP even to excellent approximation, and we have found no crack in custodial symmetry, no glaring anomaly in rates or shapes. That is not anticlimax, it is a platform. From that platform we can reach for the decimal places where new physics is likely to begin a coherent percent level tilt. Here a subtle angular distortion, there a slightly swollen tail in a high momentum distribution that refuses to go away as uncertainties shrink. And if the next surprise sits not in the decimals but in the tens of tera electron volt regime, then the Higgs guides the design of the machines that will get us there. It's both the completed keystone of a beautiful arch and the signpost pointing up the mountain path. In the end, I think the Higgs is a lesson in how the universe keeps its promises. In the 1960s, a handful of theorists wrote down a mechanism that reconciled symmetry with mass, and they predicted quietly that a scalar particle should sit at the heart of it. For decades, it was a rumor with equations. Then we built a machine the size of a city, learned to hear a signal hidden under 1,000 other sounds, and there it was, a little bump at 125 giga electron volts, with the right decays and the right spin and the right smile. That is not just a discovery. It is a demonstration that mathematics, symmetry, and careful measurement can reach into the fabric of reality and come back with something true. And because it is true, it becomes a tool. We can now use the Higgs to test, to measure, to search, and to imagine with more focus. The next chapters, self-coupling maps, second-generation couplings, nailed rare loops, tamed portals, tested machines, designed, will not be written in headlines every week. They will be written in patient progress, in collaborations that span continents and careers, and in the quiet tightening of error bars. If you have a love of science that is equal parts imagination and respect for evidence, this is a glorious place to be. We're not lost in the dark. We're walking by starlight slowly, carefully towards a horizon we can describe with a compass we built ourselves from symmetry and experiment. And the Higgs silent, and everywhere is both the ground under our feet and the tune we follow. Let's take another step and let the Higgs story breathe a little more, because the deeper you go, the more it rewards you with a sense of coherence, as if the universe has been quietly consistent all along, and we've only just tuned our ears to hear it. We've spoken about the Higgs field as a background that is on everywhere, about mass as a measure of how strongly a particle couples to that field, and about the Higgs boson as the fleeting ripple we can create when we inject enough energy into a tiny region of space. We've explored the headline couplings, the rare loops, the self-interaction, and the way precision is now our compass. Today, I want to thread a few more strands together, how the Higgs sits inside the electroweak theory with almost architectural elegance, how we translate measurements into meaning, how the strong force shares the stage in setting the mass of ordinary matter, how the Higgs brushes against cosmology and gravity, and how very practically we intend to push our instruments to hear fainter notes. Begin with the architecture, because it's beautiful. The electroweak theory, the part of the standard model that unifies the weak nuclear force with electromagnetism, has a symmetry at its core. If left unbroken, that symmetry would force the W and Z bosons to be massless, and the weak force would reach across the universe like light does. But the world patently isn't like that. The Higgs field settles into a non-zero value everywhere, and in doing so, it hides, not breaks in the destructive sense, but hides the symmetry. Three massless excitations that would ordinarily announce themselves as Goldstone bosons are instead absorbed by the W and Z, which thereby gain a new polarization state, and with it mass. The photon corresponds to an unbroken direction in the symmetry space and remains massless. There is a subtle custodial symmetry that in the minimal theory keeps the W and Z masses in a very particular relation. Precision tests, measurements of the Z boson's properties of the W mass of scattering processes at high energies are exquisitely sensitive to any violation of that relation. The fact that they keep agreeing with the minimal Higgs setup is not dull bookkeeping, it's a steady drumbeat, telling us we've set the pillars in the right place. Next, how do we make agreement or deviation precise? For many years we used a simple language where each Higgs coupling was scaled by a factor, call it kappa, relative to its standard model value. It's intuitive. Does the Higgs talk to W and Z a little more, or a little less than expected? Does it talk to bottoms and taus a little more, or less? Do the rates into photons and Z photon match the loop predictions? That kappa framework is still useful for headlines. But as the data mature, we increasingly shift to a more systematic language effective field theory, where we write down every tiny deformation allowed by symmetry and fit them globally. That gives us not just how much, but of what kind. Is there a small admixture of CP-odd behavior in the Higgs interactions with the weak bosons? Are there momentum-dependent corrections that only show up when the Higgs is produced with very high transverse momentum? Do angular correlations in the 4-lepton channel drift ever so slightly away from the pure scalar template? The virtue of this language is not fashion, it's accountability. It lets us gather evidence from many processes: gluon fusion, spectra vector, boson fusion topologies, associated production with W divided by Z, and top rare decays into one consistent fit. A genuine pattern, if it exists, should rhyme across channels. All of that rides on our ability to measure not only how often, but how. The way Higgs events populate phase space carries delicate information. In vector boson fusion, for instance, the two forward jets act like bookends for the interaction. The rapidity gap between them, the paucity of extra radiation in the central region, the azimuthal angle between the jets, these are not incidental. They're the syllables in which the interaction tells you its tensor structure. In gluon fusion with an extra jet, the high momentum tail is a magnifying glass for whatever is running in the quantum loop. Chiefly the top quark, but also anything heavy and charged that might exist just out of reach. Associated production, with a top anti-top pair puts the top Higgs interaction on stage directly where one can test not just the strength, but the handedness of the coupling. Is it purely scalar, or is there a sliver of pseudo-scalar character that would spell new physics? None of these questions are answered by a single count. They're answered by shapes and correlations, and the way those play against state-of-the-art theoretical predictions. Now a clarifying detour, because it's easy to let the Higgs drown out the strong force in the conversation about mass. Most of the mass of ordinary matter of you and me, of tables and trees, does not come from the Higgs directly. The electrons around atoms do get their tiny rest mass from the Higgs, and the up and down quarks inside protons and neutrons get theirs that way too. But the bulk of a nucleon's mass is the energy stored in the gluon fields that bind quarks together. Quantum chromodynamics is a restless, confining theory. Quarks cannot be isolated. Gluons carry the force and interact with each other. The vacuum is anything but empty. In that buzzing, self-interacting maelstrom, energy accumulates, and by Einstein's relation, energy contributes to inertia. So in a sense, the Higgs gives us the ingredients, non-zero quark masses, heavy W and Z, that make the weak force short-ranged, and QCD cooks the meal. The two are not in competition, they are complementary chapters in the book of why matter has heft. On the frontier where particle physics touches cosmology, the Higgs is a gentle but persistent presence. The electroweak phase transitioned the moment the Higgs field rolled from the top of its potential to the valley, as the early universe cooled, sets the stage for everything that followed. In the simplest version of the theory for the measured Higgs mass, that transition is a smooth crossover. Smoothness is wonderful if you like calculability, less wonderful if you're hoping the transition itself created more matter than antimatter. If, however, the Higgs sector is larger, if there are extra scalar fields, then the transition could be strongly first-order bubbles nucleating and expanding walls sweeping the cosmos conditions naturally out of equilibrium. If, in addition, there are new sources of CP violation in that extended sector, then the ingredients for electroweak baryogenesis are on the table. That scenario leaves fingerprints, altered Higgs couplings at colliders, new light scalars, and in the cosmic background a possible symphony of gravitational waves at frequencies that future detectors could hear. It is a delicious prospect. A slightly tilted coupling measured in a detector on Earth whispers about a phase change in the first fractions of a second of cosmic time, and space-time itself hums the harmony. Even in a quieter, more conservative reading, the Higgs keeps us honest about the stability of our vacuum. With the measured values of the Higgs mass and the top quark mass, a calculation suggests that our vacuum may be metastable, perched in a valley that is not the deepest possible, but with a lifetime so extravagantly long that it makes the age of the universe look like a coffee break. That is not a cause for alarm, it is a cause to measure better. The precise position depends sensitively on the top mass and the Higgs self-coupling. Thus, improving our knowledge of those is not academic fussiness. It decides which line we draw on the map of possibilities deep in the safe valley near the ridge, or just over it in a long-lived hollow. What about gravity? Here lies one of the deepest puzzles we know how to state the vacuum energy problem. If you naively add up the zero-point energies of quantum fields, the jitter that remains even in their lowest energy state, you get an absurd result. Gravity, which couples to energy, ought to see that and either fling the universe apart or crush it. Instead, the observed dark energy is tiny by comparison, yet non-zero, gently accelerating the expansion today. The Higgs contributes to that theoretical tally. We cannot simply subtract it away by fiat. Gravity does not respect our desire for convenient accounting. So the Higgs does not solve the cosmological constant problem, but by putting concrete numbers on the Higgs sector, it sharpens the mismatch. Sometimes progress in physics looks like making the mystery harder to ignore. Let's shift from grand puzzles back to the bench and talk about how practically we mean to hear more. The present Hadron Collider will enter a high luminosity phase, in which the number of collisions recorded will grow dramatically. That is both a blessing and a challenge. With more collisions come rarer processes, Higgs pairs, Higgs with top pairs in unusual final states, rare decays that move from the realm of speculation to the realm of measurement. But with more collisions also comes pileup, many interactions layered in the same event, which threatens to blur the picture. The experimental response is wonderfully inventive. New timing layers capable of tagging each charged particle to within tens of picoseconds allow you to separate interactions that occurred just a few millimeters apart along the beamline because they happened at slightly different times. Upgraded silicon trackers with finer granularity and less material reduce confusion and improve momentum resolution. Trigger systems, the fast eyes that choose which events to record at all, are being redesigned to include tracking information at the very earliest stage, allowing much sharper selections in a crowded environment. Calorimeters are being given new electronics so they can sample and discriminate pulses, more finely teasing photons from overlapping showers. These are not cosmetic upgrades, they are the difference between a story you can tell and noise you cannot pass. Beyond that, there are machines whose very design philosophy is to love the Higgs. An electron-positron collider tuned to the energy where Higgs Z production is maximal turns Higgs physics into a counting experiment with extraordinary cleanliness. You reconstruct the Z boson with precision either through its charged leptons or its hadronic decay, and infer the presence of the Higgs by momentum conservation, even if the Higgs decays invisibly. That gives you absolute coupling measurements and a model-independent handle on the total width. A circular machine promises very large statistics. A linear machine promises higher energies opening top, Higgs studies with clarity. High-energy proton colliders go after a different prize, direct access to heavy new states and high-momentum tails where deviations grow. And then there is the boldest idea, a muon collider. Muons are point-like, like electrons, but heavier, which makes radiative losses much less severe. In principle, you can aim the beam so precisely that you scan directly across the Higgs resonance in the S-channel, measuring its line shape and couplings as if you were doing spectroscopy on an atom. The technical challenges are formidable, producing cooling and accelerating muons before they decay, handling intense backgrounds, but the reward is a microscope focused on the scalar itself. Different machines, different philosophies count exquisitely, reach boldly, or zoom in like a spectroscopist. History suggests we will need all three approaches in sequence if we want a complete picture. Tucked inside all of this is the flavor question, which I think is one of the quiet marvels of the Higgs program. In our equations, the Yukawa couplings, the numbers that set how strongly each fermion couples to the Higgs, span many orders of magnitude for reasons we do not understand. The top quark's coupling is close to 1. The electron's is tiny. Neutrino masses are so small that if they came directly from the same mechanism, the corresponding couplings would be comically minute. Hence the appeal of seesaw ideas with heavy right-handed neutrinos. What the experiments have begun to do is to turn that column of input parameters into a collection of measured observables. We have strong evidence for the bottom and tau couplings. We've seen the Higgs whisper to the muon, we are sharpening our ears for charm. Plot coupling versus mass on a log scale, and the points lie along a line. It's almost childishly simple, and for that reason slightly moving. We don't know why the numbers are what they are, but we can confirm that they are all written in the same hand. There is one more aspect of the Higgs I love to emphasize, because it connects the heroic and the humble. The discovery and study of a short-lived scalar at 125 giga-electron volts demanded technologies that didn't exist when the idea was born. Superconducting magnets colder than deep space. Silicon sensors that can see a particle's birthplace displaced by a few millimeters and do it 100 million times a second. Data pipelines and algorithms that can recognize the pattern of a tau decay at the instant it happens and keep that event while discarding 1,000 others. Those tools wander. The timing layers and reconstruction tricks become medical imaging advances. The dosimetry and beam control become better radiation therapies. The pattern recognition methods become broadly useful in data-rich industries. We don't pursue the Higgs to build scanners, but when you learn how to see, you tend to see more than you set out to. So where are we now if we're honest and careful? We have a scalar particle with spin 0 and even CP mass around 125 giga-electron volts, couplings to W and Z and to third-generation fermions that match the standard model at the percentage level, a whisper small coupling to muons now within reach, and a total width so narrow we can only trap it indirectly again, consistent with expectations. We've not found exotic decays or extra scalars that force us to redraw the map, but we've fenced in many possibilities and sketched the routes by which we could discover them if they exist. A subtle excess in high momentum tails, displaced decay, indicating a hidden sector, a coherent pattern across loop-sensitive channels, hinting at heavy charged particles. We've turned the Higgs from a rumor into a working instrument. And that, to me, is the most satisfying transformation. In the 1960s, the Higgs mechanism was a beautifully economical answer to a brutally simple question. How can a symmetric set of equations describe a world where some force carriers are heavy and one light's photon is not? The price of that answer was a prediction there should be a scalar particle whose properties are tightly interwoven with the rest of the theory. Decades later, we have it, It behaves so far exactly as the mechanism demands. Now we're using it. We're using it to test the deepest symmetries we can write down. We're using it to ask whether the vacuum we inhabit is perched in a long-lived hollow or nestled deep in a valley. We're using it to listen for faint conversations with a dark sector that otherwise ignores us. We're using it to plan new instruments, precision factories, discovery engines, spectroscopes for scalars that will carry this work forward for a generation. If you love science not only for its drama but for its patience, this is a wonderful place to be. The Higgs is no longer a single headline, it's a program. It's the quiet field that makes matter tangible, and the quiet promise that if we keep measuring with care, the universe will keep telling us the truth. And that in the end is all we can ask from nature, not that it be simple in our sense, but that it be consistent in its own. The Higgs is the consistency made manifest everywhere, invisible, essential, and now gloriously in our hands. Let's turn the Higgs story ever so slightly and look at it from a new angle, the angle of necessity. Why must there be a Higgs-like degree of freedom at all? Why isn't it merely a neat trick that nature could have done without? This is one of those questions where a simple calculation done in words becomes a compass. Imagine colliding two W bosons head-on at very high energy and focus on their longitudinal polarization, the mode that loosely speaking points along their direction of motion. In a world without a Higgs field, the probability amplitude for those longitudinal W's to scatter grows with energy. Keep turning up the dial and the amplitude wants to exceed unity, which would violate unitarity, the bedrock rule that probabilities never add up to more than one. Something has to intervene to tame that growth. In the standard model, the something is precisely the exchange of a scalar with just the right couplings to the W and Z bosons. Its contribution cancels the dangerous growth, restoring unitarity and saving quantum field theory from eating itself at high energies. This is not decoration, it's structural. The same logic appears in the Goldstone equivalence theorem. At high energies, the longitudinal components of the W and Z behave like the Eaton-Goldstone modes from the Higgs field, and their scattering reveals the geometry of the Higgs sector. If experiments had found that WW scattering kept rising too quickly, we would have known that either the Higgs field was different from the minimal one, or that new dynamics, perhaps resonances from a strongly interacting sector, had to be present to do the job. Instead, nature has been wonderfully consistent. The rates and angular patterns we measure whisper that the cancellations are working as designed. The Higgs is not just allowed, it is in this sense required. That necessity reaches down into the fermion sector too. The way quarks and leptons gain mass is through Yukawa couplings, mathematical terms in the Lagrangian that tie each fermion field to the Higgs doublet. When the Higgs field acquires its vacuum expectation value, those terms turn into mass terms. It's clean, predictive, and crucially it keeps the electroweak gauge symmetry intact in the equations. Try to give fermions mass by hand without a Higgs field, and you break the symmetry, explicitly spoiling the very structure that makes the theory calculable. So the Higgs mechanism is not merely an origin story for the W and Z, it's a consistent way to let fermions have mass while preserving the elegance of the gauge framework. The price is a ledger of couplings, one per fermion species, that we must measure and eventually explain. This is where the flavor puzzle sits, quietly smiling at us. Line up the Yukawa couplings on a logarithmic axis, and they span many orders of magnitude from the almost unity top quark down to the whisper small electron with muon tau strange charm and bottom stepping along the slope. The standard model simply accepts these as inputs numbers set by nature, but it's very hard to believe those numbers have no deeper story. Some proposals imagine new horizontal symmetries broken in patterns that generate the hierarchy. Others place different fermions at different locations in an extra spatial dimension so that there are overlaps with the Higgs profile and hence their couplings differ. Still others draw on new strong dynamics that bind constituents into what we perceive as the Higgs and imprint hierarchies on the couplings. None of these ideas is yet demanded by data. All of them predict small fingerprints in Higgs processes, particularly in second-generation couplings and in rare decays. That is why the observation of the Higgs decaying to muons faint, though it lands with such satisfaction. It says the same rule that writes the top quark's coupling is quietly at work 2 families down. Charm is the next rung. Electron would be the dream. A muon collider, by producing the Higgs directly through the muon Yukawa, would turn that faint line into a headline. Let's return to the geometry that underlies electroweak symmetry breaking, because a picture helps. The famous Mexican hat potential is more than a metaphor. It's the energy landscape of the Higgs field. At the symmetric point, the top of the hat, the curvature is negative and the state is unstable. The field rolls down to the circular valley at a radius set by the vacuum expectation value, around 246 gigaelectron volts in particle physicist units. Fluctuations around the valley correspond to the physical Higgs boson. The directions along the valley were the goldstones that became the longitudinal W and Z. So far, so standard. But small variations on this theme open whole families of possibility. If the Higgs is not an elementary field, but a composite object, perhaps a pseudo-Nambu goldstone boson of a new strong sector, then the hat is not strictly fixed by a simple quartic potential. It is generated dynamically, and its curvature and shape can be slightly different. The Higgs self-coupling would then deviate the couplings to W and Z, would be rescaled by factors related to vacuum misalignment, and the high momentum tails of processes like Higgs plus jet might bulge or dip. These are delicate effects, but precisely the kind that a high luminosity collider and a precision Higgs factory can chase down. On the other side of the spectrum sit models with more Higgs fields. The simplest extension is the 2 Higgs doublet model, which introduces a second scalar doublet. Immediately you gain additional physical Higgs bosons, extra neutral scalars, 1 CP, even 1 CP odd, in the simplest CP conserving case, and charged Higgses. The couplings of the observed 125 GeV state can then differ slightly from the standard model expectations because it is a mixture of the 2 doublets. The pattern of deviation stronger to leptons, weaker to down-type quarks, or vice versa, depends on how the 2 doublets share the job of giving mass to fermions. There can also be new CP violating phases that alter angular correlations in Higgs decays and show up as electric dipole moments of the electron or neutron. And crucially, the structure of the scalar potential can change the electroweak phase transition in the early universe from a smooth crossover into a strongly first-order transition with bubble nucleation and expanding walls, exactly the kind of out-of-equilibrium physics that electroweak baryogenesis needs to tip the cosmos toward matter. This is why precision Higgs physics EDM searches and future gravitational wave observatories form a triangle. Each corner informs the others. If you prefer a different twist, consider the Higgs portal idea that the Higgs field is the one neutral bridge through which a hidden sector can talk to us. Because the Higgs couples to mass and is a scalar, it can mix with singlet fields that do not carry standard model charges. The effect is to dilute the visible coupling's open exotic decay modes, and in some scenarios produce long-lived particles that travel centimeters before decaying, leaving telltale displaced vertices in the detector. These signals are spectacular, precisely because the standard model background is so quiet in those regions of analysis space. They also require a different style of experimental imagination, triggers that don't assume everything happens promptly, reconstruction algorithms that can cope with tracks that begin far from the beamline, and detectors instrumented with precision timing so that you can separate genuine delayed decays from pile-up mischief. The program to search for such signatures is already rich and will only thicken as the datasets grow. Let's talk for a moment about how we translate measurements into meaning with intellectual honesty. For years, the Kappa framework offered a clean headline scale, each Higgs coupling up or down by a factor, and see whether the fit prefers a deviation. It remains a useful lingua franca for summaries. But the field has matured into effective field theory (EFT) as the main language for precision. In EFT, you write every operator, every little deformation of the interactions allowed by the symmetries up to a given order with coefficients to be determined by data. That allows one to capture not just rescalings, but new Lorentz structures, tiny CP-odd admixtures, momentum-dependent pieces, and to correlate what happens in Higgs processes with what happens elsewhere. Triple gauge couplings, electroweak precision observables, even certain flavor processes. It is a disciplined way to let the data tell you whether there is a consistent pattern. If a pattern appears, you can then reverse engineer what heavy new particles or forces would generate exactly those operators when integrated out. If it does not, you push the bounds further and keep the standard model in its well-earned place of honor. Behind all of this is the question of naturalness, the aesthetic but technically sharp discomfort with a light scalar mass. Quantum fluctuations from every particle that couples to the Higgs field want to drag the Higgs mass up towards the highest scale in the theory. If that scale is truly enormous, then keeping the Higgs down at 125 gigaelectron volts requires cancellations among large contributions. Perhaps that is simply the way the world is. Or perhaps there is symmetry. Supersymmetry is the canonical example ensuring that each dangerous contribution is cancelled by a partner's contribution of the opposite sign. Or perhaps the Higgs is composite, and its mass is protected because it is a pseudo-Goldstone boson of a larger symmetry. Or perhaps there is neutral naturalness, where the partners live in a mirror sector uncharged under our forces and thus difficult to produce directly. Each idea comes with concrete consequences for Higgs couplings, high momentum distributions, and the spectrum of additional states. The absence of dramatic discoveries so far has squeezed many popular corners, but it has not closed the question. It has, however, turned taste into test naturalness. It is no longer a philosophical debate, but an experimental campaign. You might ask, where does gravity enter this picture beyond the broad musings about vacuum energy? There is a bold line of thought, Higgs inflation, that explores whether the Higgs field itself, with a non-minimal coupling to curvature, could have driven the early exponential expansion of the universe. It is an elegant economy of ideas. One field does two jobs. But that elegance is fragile. The proposal leans on extrapolating the Higgs potential to energies far beyond what we can test, and on assuming that quantum corrections and higher dimension operators remain kind. The honest state of play is that the idea is intriguing, constrained by measurements of the cosmic microwave background statistics, and very much not settled. It's a good example of how the Higgs connects to cosmology in ways that are both alluring and perilous, easy to write down, hard to make watertight. Let's ground ourselves again in the laboratory, because in the end this is an empirical science. What will the next decade actually do? The high luminosity running of the collider will multiply the Higgs sample many-fold. That opens doors to Higgs pair production, which is the gateway to measuring the trilinear self-coupling. In practice, one hunts final states like 2 photons plus 2 bottoms, or 2 taus plus 2 bottoms, and even 4 bottoms with heroic flavor tagging. 2 quantum mechanisms, box and triangle, contribute, with the triangle carrying the self-coupling. Their interference makes the total rate exquisitely sensitive to that coupling. A precise measurement there tells us the curvature of the potential, which in turn feeds back into questions of vacuum stability and the thermal history of the universe. Simultaneously associated production with a top-anti-top pair will be measured with increasing precision, giving a direct handle on the top Higgs interaction, including the possibility of tiny CP odd components. Vector boson fusion becomes a mainstay of differential studies, probing subtle momentum-dependent corrections in the couplings to W and Z through the characteristic forward jets and clean central region. And loop-sensitive rare decays, 2 photons Z plus photon, serve as periscopes looking for heavy charge states that we cannot produce directly, but that still leave ripples in the rates. On the instrumentation side, the detectors are being taught new tricks. Precision timing layers, devices that can timestamp charged particles to tens of picoseconds, will let analysts separate pile-up interactions from the primary collision by their arrival times, effectively adding a time axis to the reconstruction. Silicon trackers will be finer and faster. Calorimeters will read pulses more sharply. Triggers will do pattern recognition in real time. These sound technical because they are, but they are also the reason we will be able to keep seeing a crisp Higgs peak in 2-photon spectra when the event environment is busier than a city at rush hour. And beyond the current machine design, studies for future colliders are animated by the Higgs. An electron-positron Higgs factory operating where Higgs Z production is maximal offers model-independent coupling extractions and sensitivity to invisible decays by reconstructing the Z and inferring the Higgs by recoil. A circular machine promises enormous statistics. A linear machine buys higher energies for clean, top Higgs studies. A very high-energy proton collider would extend discovery reach into the tens of tera electron volts, where heavy partners might hide and where longitudinal WW scattering could be mapped in detail. And a muon collider, the most audacious of the lot, would let us scan directly across the Higgs resonance in the S-channel, measuring its line shape like an atomic spectroscopist measures a transition. Each concept is a different bet on how the next surprise will present itself, as a tiny percent-level tilt, requiring exquisite cleanliness, as a heavy new state needing brute energy, or as subtle structure in the scalar itself. Let me end this turn with a gentle reminder of scale. The Higgs vacuum expectation value sets the scale for the masses of the W and Z, and through the UQARs for the quarks and charged leptons. Yet most of the mass of ordinary matter, the heft in your hand, comes from the frantic energy of the strong force gluing quarks into protons and neutrons. The Higgs is the scaffolding that lets that strong force architecture exist in a universe where the weak force is short-ranged and electrons are not massless. That is a beautifully layered picture fields, begetting particles, symmetry hidden rather than destroyed mass, emerging not as a primitive ingredient, but as a consequence of interactions with a field that is switched on everywhere. We did not know the world would be this way. We asked it carefully, and it told us. So, where are we truly? We have a scalar of spin zero, and even CP mass, around 125 giga electron volts. Its couplings to W and Z, to bottom and tau, and even to muons line up with the simple rule proportional to mass within the precision we now command. Its total width is so narrow that we trap it indirectly and still find agreement. We see no extra scalars marching in formation, no dramatic exotic decays, but we have fenced in many such possibilities and mapped where to look next. We have not yet pinned the self-coupling with high precision, but the door is opening. We have begun to probe whether the top Higgs interaction is purely scalar or carries a whisper of CP violation. And we have a coherent plan, precision factories, discovery engines, spectroscopic lenses to keep asking sharper questions. If you love science for the way simple ideas become necessary, this is a golden age. The Higgs began life as a clever mechanism written on paper. It has become a measured component of reality and a tool we now use to interrogate that reality further. It is the quiet field that makes matter tangible, and the quiet invitation to keep going, measure a little better, think a little more clearly, and see whether the universe, which has been so consistent so far, is about to show us where the next layer of structure begins. Let's keep moving, and I'll try to make the next turn of the Higgs story feel both inevitable and surprising, like finding an elegant proof hiding inside a messy calculation. We've said the vacuum isn't empty. It's quietly filled with a field that is on everywhere. We've said mass is not a dollop of stuff, but the strength with which a particle couples to that field. We've said the Higgs boson is the fleeting ripple we can coax from that field when we focus enough energy into a point. All of that is the broad picture. Now I want to do three things at once. Show you why this machinery is not optional. Show you how intimately it is woven into quantities we can measure with ridiculous precision. And then step back far enough that you can see how the whole construction sits inside the wider physics of matter stars and the early universe. First necessity, but in a new light. Earlier we talked about longitudinal WW scattering and the way a scalar with exactly the right couplings arrests the otherwise perilous growth of the amplitude with energy. That argument sits on a deeper identity called the Goldstone equivalence theorem, at energies much higher than the W and Z masses. Their longitudinal components behave like the Goldstone modes that were eaten when the Higgs field turned on. In plain words, the high energy behavior of the weak force is a window straight into the geometry of the Higgs sector. If the geometry is the simple Mexican hat of the minimal theory, the dangerous terms cancel with exquisite precision. If the hat is warped because the Higgs is composite or because there are extra scalar fields, those cancellations are imperfect. How do we check? We don't yet smash beams of on-shell Ws together, but proton-proton collisions frequently produce pairs of W or Z bosons that scatter off each other before they decay. This vector boson scattering leaves a telltale signature 2 energetic forward jets with a big rapidity gap and a relatively quiet central region. By measuring rates and angular patterns in these events at ever higher energies, we are in effect testing whether the Higgs field is doing its unitarity restoring job with the right grace notes. The fact that everything we see so far lines up with the minimal design is not boring. It is a very strong statement that the geometry of electroweak symmetry breaking is close to the textbook picture. Second, the Higgs is not just a story about massive force carriers and exotic colliders. It is baked into constants we meet on page 1 of particle physics. Take the Fermi constant, the number you infer from the lifetime of the muon. That constant sets the overall strength of the weak interaction at low energies. In the electroweak theory, it is directly related to the Higgs vacuum expectation value, the height of the brim on the Mexican hat. So when you measure how long a muon lives, you're reading off the same cosmic parameter that sets the W and Z masses, and that appears in every Yukawa coupling. In fact, once you know this vacuum value, call it VVV, a fermions coupling to the Higgs is essentially its mass divided by VVV up to conventional factors of 2 and square roots that we can spare ourselves for now. That is why the plot of Higgs coupling strength versus particle mass is such a satisfying straight line across many orders of magnitude. It's one number, the Higgs vacuum value, tying the ledger together. The same value is pumping quietly through every atom in your body, every neutrino that passes through you, and every beta decay in every star. It's worth pausing to feel the reach of that single number. If VV were larger, all the weak boson masses would be larger, and the weak force would be even shorter ranged. Radioactive processes in stars would be slower. The chain of nuclear reactions that builds the periodic table would run with different timings and outcomes. If VV were smaller, the weak force would reach farther and act faster. Stellar lifetimes, supernova mechanisms, even primordial nucleosynthesis would change. Chemistry would inherit a different set of stable isotopes, and biochemistry might never have had the same playground. We sometimes call the Higgs field switched on everywhere, which can sound abstract. But you can think of VVV as a dial, and the position of that dial is one of the universe's most consequential settings. The discovery of the Higgs boson isn't just the detection of a ripple, it's the direct confirmation that this dial is real and set, where the rest of physics has been quietly assuming it sits. Let me make the connection to ordinary mass even more concrete, because this is where two magnificent stories meet. Most of the mass of a proton or neutron is not the sum of the tiny masses of the quarks inside, it is the energy of the strong force binding them. Quantum chromodynamics is a confining, self-interacting field theory. Gluons carry the force and also feel it. Quarks are never seen in isolation. The vacuum is a buzzing medium full of virtual activity. The energy in that bound state contributes inertia via Einstein's E equals mc2, E equals mc circumflex 2, E equals mc2, and that energy is the lion's share of the weight of everyday matter. So the Higgs is not the source of all mass. Rather, it sets the rest masses of quarks and leptons and the range of the weak force, and then QCD takes those ingredients and builds heavy nucleons out of energetic fields. The two stories coexist. The Higgs provides the scaffolding, the strong force furnishes the bricks and mortar. Now to precision, because this is where the field has quietly become a metronome. Here you list every tiny deformation of the interactions allowed by symmetry terms that slightly tilt a coupling, add a whiff of CP-odd behavior, or make an interaction depend on momentum in a new way, and you fit them globally across many processes. When you do the global fit, you're no longer asking, is this rate high or low, but is there a consistent pattern across everything? That consistency, or the first crack in it, is how new physics will most likely introduce itself now. Some of the most delicate clues live in the tails, the high momentum corners of phase space where loop effects and contact interaction deformations grow. In gluon fusion, Higgs production, with an accompanying jet the shape of the Higgs transverse momentum spectrum at very high PTP. TPT is a magnifying glass on whatever is running in the quantum loop in the standard model. It's the top quark. If there are heavier charged particles hiding above direct reach, they could leave a little tilt here. In vector boson fusion, the rapidity gap between the forward jets and the azimuthal angle between them are sensitive to the tensor structure of the Higgs vector-vector vertex. A tiny CP-odd admixture would smear those patterns just so. Associated production with top quarks lets you interrogate the top Higgs interaction directly, including whether it is purely scalar, as expected, or carries a hint of handedness, a pseudo-scalar sliver that would herald new CP violation. That makes their rates exquisitely sensitive to any unknown heavy charge particle that could also run in the loop. The measurements so far are in warm agreement with the standard model, but every new decimal place on those branching fractions is a test of the unknown. In the Mexican hat picture, it's the curvature of the brim in the radial direction, how stiff the field is when you push it up and let it fall back. In equations, once you know VVV and the Higgs mass, the trilinear self-coupling is fixed in the standard model. Measuring it is hard because the portal is Higgs pair production, and the quantum roots to two Higgs bosons, box and triangle, interfere in a way that leaves the total rate small and delicately dependent on that coupling. The cleanest channels combine one very clean decay, two photons with one very common one, two bottoms or two taus with two bottoms, or if your flavor tagging and jet substructure are masterful four bottoms. It is a heroic measurement. But the prize is real. That single number plugs straight into our picture of the Higgs potential, into questions of vacuum stability, and into the thermal history of the early universe. If the self-coupling is even slightly off, the electroweak phase transition could tip from a smooth crossover to a strongly first-order story of bubbles and walls, precisely the conditions some models need to explain why the universe is made of matter rather than antimatter. It would also hint at cousins of the Higgs extrascalars waiting in the wings. Speaking of cousins, there are two broad classes of extended Higgs ideas to keep in view. In one class, the Higgs is not elementary, but composite a bound state of a new strong sector, often a pseudo-Nambu-Goldstone boson of a larger broken symmetry. In that case, the couplings to W and Z are typically slightly rescaled by a factor related to a new compositeness scale, and high momentum tails in Higgs production can bulge or dip in characteristic ways. New resonances associated with the strong sector may sit at a few to 10 trillion electron volts, reachable only by future high-energy colliders, but their footprints appear already in precision fits. In the other class, the Higgs sector is enlarged with additional fields. The simplest is two Higgs doublet models, which bring along extra neutral and charged Higgs bosons, and can change the pattern of couplings for the one we've found. Those scenarios can carry new CP-violating phases, feed electroweak baryogenesis, and open exotic decays. Both classes share a virtue: they make concrete testable predictions for percent-level shifts and rare processes that the LHC's high luminosity era and future Higgs factories can hunt down. Let's talk instruments, because ideas demand the right ears. The current collider entering its high luminosity phase will deliver staggering samples. That alone transforms possibilities into measurements, di-Higgs rates, top associated production in rare final states, and vector bosons scattering at higher energies. But the environment will also be busier, many simultaneous interactions per bunch crossing that would blur the picture if not for upgrades as ingenious as any in physics. New timing layers that stamp charged particles to tens of picoseconds, so that you can separate interactions by their arrival times. Silicon trackers with finer granularity and lower mass. Calorimeters with faster, more precise readout. And trigger systems taught to recognize complex patterns in real time. These are not luxuries. They are the difference between a crisp 2-photon Higgs peak and noise. Beyond that, the community is designing machines that love the Higgs on purpose. An electron-positron collider operating where Higgs Z production is maximal turns many questions into clean counting experiments. You reconstruct the Z boson and infer the Higgs by recoil, even if it decays invisibly. You measure couplings absolutely, and crucially you determine the total width in a model, independent way. A circular design promises enormous statistics. A linear one buys higher energy for clean top Higgs studies. A next-generation proton collider, operating at tens of trillion electron volts, would open direct access to heavy partners and map longitudinal vector bosons scattering with unprecedented reach. And then there is the audacious proposal of a muon collider. Because muons are point-like and heavy, the beams can be tuned to produce the Higgs directly in the S-channel. You can, in principle, scan across the Higgs resonance like a spectroscopist measuring an atomic line. The technical challenge is producing cooling and accelerating muons before they decay. Handling intense beam, induced backgrounds are formidable, but the prize is unique, a microscope focused right on the scalar itself. Two more threads before we draw breath. One is flavor. The column of Yukawa couplings from near unity for the top to vanishingly small for the electron cries out for explanation. Horizontal symmetries, extra dimensions with separated wave functions, dynamics that generate hierarchies radiatively. These are not just labels, they are models with telltale signatures in Higgs couplings, in rare decays, and in patterns. Across families. The other thread is naturalness. Scalar masses in quantum field theory are hypersensitive to fluctuations from every particle that couples to them. Left alone, the Higgs mass would like to soar to whatever high-scale new physics lives at, perhaps the Planck scale, unless there is a symmetry or structure to keep it light. Supersymmetry composite, Higgs twin Higgs, and neutral naturalness, warped extra dimensions each, is a way to protect the scalar. None has yet forced the laboratory to admit it, none has been excluded in all of its interesting forms either. The Higgs turns this philosophical discomfort into an empirical program if protection is at work. Higgs couplings should be tipped by percents, tails should swell, extra states should appear. If no protection is at work, the world is tuned, and that too is a fact to be measured, not merely lamented. Either way, the Higgs has transmuted taste into test. So where are we after all these turns? We have a scalar of spin zero and even CP at around 125 giga electron volts, whose couplings to W and Z, to bottoms and taus, and now to muons, follow the simple rule, proportional to mass within today's precision. Its total width is too small to see directly, but corralled indirectly in line with the standard model. Loop-sensitive decays to photons and to Z plus photons sit where they should, though they keep an open invitation to anything heavy and charged that dares to tilt them. The self-coupling is coming into view through di-Higgs production. Vector boson scattering looks healthy. The top Higgs interaction seen directly in associated production appears scalar. No extra scalars have walked on stage. No spectacular exotic decays have stolen the show. But the absence of drama is not the absence of meaning. It is the platform from which percent-level patterns, if they exist, can become sentences, and sentences can become stories about physics beyond the standard model. If you love science for the way simple ideas, checked carefully, become pillars that hold up whole buildings, then this is a wonderful moment. The Higgs is not a flourish. It is the hinge that lets the electro-weak door swing open the dial that sets the weak scale, the straight line that ties masses to couplings, the quiet field that gives the world its particular texture. We can weigh it, time it, watch it pair with itself, and ask whether it speaks, however softly, to sectors of the universe that otherwise ignore us. And we can design instruments with the explicit brief, take this scalar seriously. That is what a mature discovery looks like, not just a banner headline, but a program of work that spans decades, touches cosmology and chemistry, and rewards patience with clarity. From here, the natural next step is to watch the Higgs talk to itself with higher fidelity, to nail the second-generation couplings, to lean on loop-sensitive modes with sharper theory predictions, and to keep vector bosons scattering under a magnifying glass as energies climb. Somewhere in that weave, a coherent percent-level tilt, a displaced decay, a bent tail, may be the first unmistakable hint that the scalar we've met is the front door to a larger house. And if it isn't, if the pattern continues to be simple and clean, then the lesson is just as profound. The universe sometimes really does choose the minimal, elegant mechanism. Either way, we learn carefully, quantitatively, beautifully.